Okay, so in front of me I have two of the classical recommendations for classical mechanics. Aha. So we have on the left here Mathematical Methods of Classical Mechanics by V.I. Arnold. Okay? So that's this textbook here. Now on the right, we have Classical Mechanics written by Goldstein and other authors. Okay? Now these, for those of you who maybe are more math focused and don't know much about physics textbooks, these are the two most commonly cited, at least from my corner of the universe, two most commonly cited textbooks on the topic. This is a topic that I care a lot about. It's very relevant to my research, as well as just to the real world in general for obvious reasons. Classical mechanics is essentially, if you've ever heard of F equals ma, Newton's second law, you should probably care about classical mechanics. So let's just take a quick look at the table of contents here. So Arnold is going to be more mathematically oriented and is going to assume more of a math background as a result, okay? And you'll see that especially when we get into the part on Hamiltonian mechanics. So part one is Newtonian mechanics. And just keep an eye on the specific subsections of the chapters. So part two, we're getting into Lagrangian mechanics. And chapter 4 already, we have Lagrangian mechanics on manifolds, okay? And it covers Noether's theorem on manifold in a manifold case. Now, chapter 6 is rigid bodies. I will say there isn't too much on rigid bodies, which is unfortunate. Right now in my research, rigid bodies are going to be critical, understanding rotation and, inertial forces, not inertial forces, but moments of inertia and rotational motion is going to be critical. So, yeah, that is a downside of this textbook. It doesn't have much on rigid bodies. However, we move to part 3, Hamiltonian mechanics. It has a lot of Hamiltonian mechanics. That's kind of a strength of this textbook. So it starts building up the mathematical machinery. We get differential forms, chapter 7. Symplectic manifolds, chapter 8. How it builds differential forms is very from an intuitive perspective, okay? It's like a weird hybrid between like rigorous math, but also like trying to be more intuitive than a normal math textbook, just because it's trying to relate to the physicists that are reading it. Okay, then chapter 9, we have some canonical formalism here. Chapter 10, introduction to perturbation theory. And then we have some appendices. The appendices are going to sometimes be an indication of prerequisites, other times, like in this textbook, I don't think these appendices are prerequisites. They're rather just probably proofs or topics that he wanted to push aside to the appendix for whatever reason. He couldn't find a good place for them in the natural order of the text. So appendix 1 is pretty important. Appendix 1, I would say, is one of the most important concepts to me that even exists at all. So there's the table of contents by V.I. Arnold. And I'm going to go through the table of contents by Goldstein, but what I want to hear from the comments section after I go through this table of contents, I really want to know if any of you know these two books, which do you prefer, or what is your recommendation on classical mechanics? I really would love to hear from the comments section, to hear from you, your thoughts on these textbooks or on other possible recommendations for classical mechanics. Okay. So, here we go. We have Chapter 1, Survey of Elementary Principles. Chapter 2, Variational Principles and Lagrange's Equations. Chapter 3, The Central Force Problem. Chapter 4, The Kinematics of Rigid Body Motion. Chapter 5, The Rigid Body Equations of Motion. This is wonderful because there's a ton of material on rigid body motion compared to Arnold here. Chapter 6 is Oscillations. Chapter 7, The Classical Mechanics of the Special Theory of Relativity. So it's kind of One thing that the author mentions is that this textbook is kind of designed pedagogically to prepare the reader for quantum mechanical formalism. Okay? So you can see that, quantum mechanics is actually not done within the context of relativity, special relativity. But this is something that's typically taught as a precursor towards modern physics, obviously, because modern physics includes general relativity and quantum mechanics. So they're kind of they're priming you for an understanding of special relativity. And then, of course, once you get into quantum field theory, then you do need to understand. Of course, quantum field theory is going to be using special relativity. So is general relativity. Okay, Chapter 8 is the Hamilton equations of motion. Chapter 9 is canonical transformations. Chapter 10, Hamilton-Jacobi theory and action angle variables. Chapter 11, classical chaos. One thing that I love from a philosophical perspective, the butterfly theory. The butterfly theory exists in physics, which is a beautiful fact. And then we have canonical perturbation theory. This is an indispensable tool for physicists. And potentially applied mathematicians, although I'm not sure on the applied math side. Certainly that there are relations to the stability of numerical models. But perturbation theory is something you see showing up a lot in physics and not as much in math. And so it's weird. But I guess it probably shows up in math, under a different name or something that I just haven't seen yet in my education. And then the final chapter, Introduction to the Lagrangian and Hamiltonian Formulations for Continuous Systems and Fields. This is going to introduce you to the classical field theory that you will need to progress in your physics education, right? Because classical field theory is a field-oriented approach where, of course, we're viewing the motion of particles as essentially test particles in a field, and the fields themselves are the objects which satisfy some variational principle and minimize some functional in nature. Okay, well, yeah, I hope you enjoyed this video, and also, just let me know your recommendations for classical mechanics.